So here again we see this model of a celestial sphere. And celestial sphere is not the way the real deal is. But remember we said according to this model, the stars actually are embedded on this hollow sphere, and we are in the middle of the sphere. And like the caption says here, let's see if this will work for you. The Earth, we know the Earth rotates on its axis. That's why we have day and night. It takes 24 hours for it to spin on its axis of rotation once. Specifically, if you were looking down from the North Pole down, it goes counterclockwise. So you see that motion there. And it's this motion that gives the apparent motion of the stars. So actually, as we rotate, spin, we are going from west to east. Okay? That makes the stars, and frankly the sun, appear to go from east to west. Okay? And that's kind of shown here. And you might need to convince yourself of that, but that is the way that works. We're going to be talking just a little bit more about this motion. This motion has a term called diurnal motion, how the stars appear to move throughout the course of the night, and how the sun appears to rise in the east and set in the west. All has to do with the Earth spinning or rotating on its axis. So this right here, this kind of bullseye looking thing, would be looking at in the direction of one of the poles, either the North Pole or the South Pole, and these are star trails that go around the North Celestial Pole or the South Celestial Pole. So diurnal motion. Okay, diurnal motion is then, in general, things that move because the Earth is spinning on its axis. So that daily movement of stuff, whether it's the sun rising in the east and setting in the west, the moon, as the moon orbits the Earth, we don't see that. We don't see that orbit throughout the course of a day. But what we do see is the moon appear to rise in the east and set in the west because the Earth is spinning on its axis of rotation. We kind of see subtle changes in the location of the moon, specifically relative, most noticeably relative to the sun as it orbits the Earth. But the moon rises in the east and sets in the west. Okay. Now I have a figure coming up on the next slide to kind of solidify this kind of cool aspect of some stars are special stars. Some stars are so special, they are always up there. They're called circumpolar stars. They're always up there during the day, during the night, but we're going to see that these circumpolar stars need to be within that bullseye area. Okay, that bullseye we saw just a minute ago with kind of in the middle we knew was like Polaris, our North Star. So circumpolar stars need to be near Polaris, and we're going to see that some latitudes relative to the equator have more circumpolar stars than others. I'll show you what I mean coming up. This is trying to kind of emphasize a few things. One of them is the idea of circumpolar stars. So I'm going to kind of hope you found that word if you're filling in your slides. If you're having a hard time filling in your slides because I'm kind of I'm zooming in too quickly, let me know and I'll see what I can do. So hopefully you see the sun over here to the left, because I'm going to kind of move this. Now the beauty of the sun being over there to the left is actually, do you see this over here is dark blue, because actually we can't see any stars there because the sun's over here. But we can potentially see stars over here. Specifically, we have picked out a person here standing on, looks like somewhere in North America, and you can see stretched out this person's horizons. So this light blue actually is kind of his local sky, his or her local sky at the given time. We talked about zenith, that's straight up from that person. Notice we have the tilted axis of rotation here. Okay, and we can see relative to the axis of rotation these kind of movement of stars going rising in the east and setting in the west. Okay, bands of stars. Okay, so look at the person's horizon. Can you see where this band of stars right here, okay, this band of stars right here, can you see where, and here's a star on that band, actually, they will never set below the horizon. They'll keep circling right there. I don't know if that makes sense to you. But these actually are what we call circumpolar stars. Anything, and I guess put another way, I'll kind of zoom out. Put another way, that person sees the nighttime sky, and this north celestial pole, I'll go ahead and put Polaris up here. Polaris. The star Polaris is right here on the celestial sphere. And there's a bullseye right here. And all of these stars are circumpolar. They never set. I also like this slide because this is the dude's horizon down here towards the south. No matter what time of year, no matter what time of day, this person actually, there's a cone of stars that this person is never going to see. And kind of picking on this star back here, and I'm kind of making a mess out of this slide, but can you see this star on this band right here? This person will never see that star. It's below that person's horizon like forever. Okay. But boy, it's a lot easier to explain these figures if I'm in class, so I'll do my best. You're like, okay, so I see star trails and I see a polar bear, and what is the point here? Well, here's my point. If you are the polar bear, okay, one good place or possible place for you to be is right at the North Pole. I'll put NP for North Pole. Okay, and at the North Pole, we'll go ahead and we'll say that that's 90 degrees latitude. Now, I have a slide coming up to remind you what latitude and longitude are, but that's the top, that's the North Pole, 90 degrees latitude. Do you guys buy this, that as the polar bear looks up, okay, at his zenith, he is going to see the star Polaris? Why? Because Polaris is the North Star. So honestly, that this polar bear can look straight up and see Polaris. Now, around Polaris, we're going to make Polaris the middle of a bullseye, and we'll make a circle, a bigger circle, a bigger circle. And this is where I wish I was in a classroom showing you a bigger circle and a bigger circle. And eventually, our circle is going to hit the horizon in all directions. So that's why what this is showing you are star trails basically whipping around the horizon in a circle, because Polaris is at the zenith of if you're at the North Pole. Okay. My other favorite one is this one with the palm tree. Okay. This is supposed to be emphasizing, like, if you were at the equator. Okay, 0 degrees latitude. That's a declination latitude. Well, I guess that's okay. Thinking of Earth terms, latitude. So if you're at the equator, okay, this is where I get to say, where is the North Pole? Where's the North Pole? Or where, if you're at the equator, where is Polaris? And let's just pretend like we are facing east, okay? Can you see, we're facing due east. Can you see off the chart here, Polaris, or the North Pole is, north is, I'll better put Polaris, the star Polaris, okay, is right at the horizon. Does that make sense? Okay, you're trying to see Polaris, and it's right at the horizon. Okay, we're going to actually see, if we look south here, that there is no pole star, but there's a region of space where we still have the bullseye sort of thing going on. Okay, so here's the deal. Let's pick on Polaris, looking north, and we're going to make bullseyes around the star. But notice it's just going to be semicircles, and it's hard for me to show you, but I'm trying to make semicircles around the due north, the star due north, Polaris. So as I make semicircles, notice that they get larger and larger. And the semicircles, when I get to due east and west, my semicircles have become the largest semicircle possible. And they rise in the east and set in the west. Okay? So rise in the east and set in the west behind me. Then from there, I make more and more semicircles, all the way becoming smaller and smaller until I get to the South Pole region. Notice the kind of I won't say frustrating part, but there are no circumpolar stars. Circumpolar. Okay, there are no circumpolar stars if you're at the equator. You have maybe wonderful weather and palm trees, but no circumpolar stars. I want to, before I leave and go, just kind of maybe look at what our stars look like on the horizon. Can you see where the polar bear, if I were to ask you, what sort of, looking at the bullseye straight up and kind of major circles, complete circles coming all the way down the horizon, can you see where the polar bear has, all of his stars are circumpolar? Isn't that cool? I don't know. So depending upon, we've seen two extremes, at 90 degrees latitude at the pole and at 0 degrees latitude at the equator. Your star trails, or the way your stars rise and set, the angle, which they do, and your number of circumpolar stars will vary. And so here we're actually seeing, we are here in southeast Iowa about 40 degrees north latitude. So this is about 45 degrees latitude. So here's my slide to kind of remind you that here on Earth, we break the Earth up into latitude and longitude. And it's kind of, I told some students the other day, I'm just amazed that, kind of creeped out, that you can have a device and an app on your device that will tell you the coordinates, the GPS coordinates, latitude and longitude of your location at any time. It's amazing. So latitude is relative position to the equator, and longitude is relative position to actually a prime meridian. So latitude goes from 0 degrees to 90 north and 90 south, and lines of longitude actually go from the prime meridian 0 degrees, from 0 to 180 east and west. So what your author does is shows you two locations that differ greatly by latitude. So latitude, the relative position to the equator. So I hope you can see this little guy here. Looks like he's visiting that polar bear up at the North Pole at 90 degrees latitude. And you can clearly see again this light blue is his horizon. Okay, so, or excuse me, well, his possible local sky. So if we contrast that then to a location in the southern hemisphere, specifically 34 degrees south of the equator in the southern hemisphere, okay, notice that this person's local sky has changed significantly. I don't know if you buy this or not, but if you think about it and read about it and think about it some more, you can convince yourself that, for instance, if we pick on this line of latitude, anybody who is at the same line of latitude, 34 degrees south latitude, as the Earth rotates, spins on its axis for a given day, they will ultimately see a very similar or the same field of view, the same sets of constellations. Okay? Now, granted, they'll have daytime versus nighttime at different times, but they are privy to the same sets of stars. So we say that stars, I'll put it another way, stars will vary. I think this might be a homework question. Vary by latitude. Latitude. Okay. They do not vary by longitude. So if you're at a different, if you're on a different longitude but the same latitude, you're going to see the same skies.